So let's talk about the last section. There's no write-ups in this section. We're done with the write-ups. This last section is just about what we call power, the power of a test. And it's kind of a weird concept. I'm going to kind of narrow it down so you just know what you need to know. It's the probability that you correctly reject the null hypothesis. So it's the probability of rejecting the null hypothesis when it's false. Or you can think about it in terms of like probability from chapter 7. It's a conditional. That you reject the null hypothesis given that the alternate is true. So it's usually a number. Now, you will never have to find this probability. Although last year, the last AP question had them do this. But then they went back and said you could get the whole last question wrong and still get a 5. Because nobody knew how to do this. Because every textbook says you do not need to know how to do this. And then they asked the questions. So, power, what you do need to know, it has to do with type 2 error. So powers like here, type 2 error, remember that's beta. So if type 2 error is beta, the power of a test is 1 minus beta. Because these should all add up to 1. So if like the probability that you have a type 2 error is 5%, your power of your test is 95%. Okay? That's really all, most of what you need to know. The power of a test is good. If the null hypothesis is really false, we want to know that. So the higher the power, the more chance we have of detecting the truth. Right? Because this is saying you're rejecting the null hypothesis when the alternate is true. So you want a high percentage probability. So let's try an example with, and then this is going to be a little bit of a review of type 1 error, type 2 error. So suppose that the 1990 census said that 83% of Michigan residents have a high school diploma. The Department of Education believes this percentage has decreased, so they commissioned a survey to estimate the true percentage. Define the parameter of interest, state the hypotheses, describe each kind of error in context, and describe the power in context. So this would be like one of your free response questions on your test. So first thing, we're going to define our parameter. That's really condition 4 in a write-up. So P is the true proportion of Michigan residents with a high school diploma.
I have a question.
Yes.
Is this just going over like Michigan residents that are like above high school age, like adults?
Yeah, I'm assuming. I'm assuming that's what it is. So, our two hypotheses. Our null hypothesis is that P is equal to 0.83. Remember, your null should always be equal. And they're doing this survey because they think the alternate is that P is less than 0.83. So, type 1 error. Remember, you want to compare what you're saying versus what's actually happening. Okay, and you'll see when you get your quizzes back. So it's type 1, remember, is rejecting the null hypothesis when it's actually true. So saying less than 83% of Michigan residents have a high school diploma when it's really 83%. What? Rejecting this, but when this is true. So you're saying this, but this is what's the actual. You can word this differently if you want to. everybody kind of words it a little bit differently. This is usually what I check with.
Okay. Yeah.
Say less than when equal to. Okay. Yeah, it's fine if you word it differently. What I don't like is when people say reject that p equals 0.83 when it's really true. Like I want like what you're saying versus what's happening. So type 2 error is the converse. Saying 83% of Michigan residents have a high school diploma when it's really less than 83%. And make sure, and you'll see this when you get your quizzes back, that you match your alternate hypothesis. So I need to see less than. If this was greater than, I'd want to see greater than or different. Okay, so the power of the test in context is the probability we correctly reject the claim that 83% of Michigan residents have a high school diploma. So basically, the power of the test is the probability that you're right, that you're going with the alternate. Okay, so you just need to know that it's 1 minus beta, and you need to know what affects power. Power is more of like, on the test, it's usually like a multiple choice question. Like I said, last year they made it a free response question and they had to knock that question out. So it's going to be more on the multiple choice. So you have to know what affects power. So power of a test can be higher. You can change it if you increase the significance level. Okay, remember, alpha and beta are inverses. So if alpha increases, beta will decrease. Well, power is 1 minus beta. So that means that power then increases. So it's like a up, down, up. So if you increase your significance level, you increase your power. You can increase your sample size. Because remember, when you increase your sample size, you decrease alpha, but you also decrease beta. So if you're decreasing beta, that means your power is increasing. And we've talked about these before in terms of alpha and beta. Now, the one thing we haven't really talked about yet that works with power is that there's what we call a larger effect size, meaning there's a larger discrepancy between the null hypothesis and the true value. So like, okay, let's think about an example. This is the easiest way to explain it. Let's pretend we're looking at cost of college textbooks, which you will find out are super expensive. Okay, let's pretend our null hypothesis is that the mean is, on average, $300. The alternate is you think you're going to spend more than $300. Again, we're comparing versus what we're trying to find is the true actual cost. So if the true mean was 301, the probability we reject the null hypothesis is not great, because 301 is really close to 300. You can't see that. I probably should word that differently, but whatever. since 300 is close to 301. So that's a small effect size, that the actual value, the actual true average cost of textbooks is close to what you're trying to prove. Now, if the true mean was 350, the probability we reject the null hypothesis is better, since 350 is far away from 300. So that we'll make the correct decision. Now, can you really change a lot of this? Not really. You just hope you pick a good value here that's farther away than what you want. Okay? Yes,
What would you consider close?
Within, like, well, it depends. Like a proportion, a couple percentages, a mean, a couple of whatever the units are. Yeah, this one's harder to change. But these you can change. Okay, questions on power. Again, you just need to know that it's 1 minus beta and know that it's rejecting the null hypothesis when the alternate's true. It's the probability. And know what affects it. Okay, the last thing is, so chapter 9 was all about confidence intervals. Chapter 10 is all about hypothesis tests. They are related to each other. So this is how they're related. Again, multiple choice questions. Hypothesis tests are designed to answer the question, am I surprised by the observed data? How surprised? So the answer is based on your p-value. So you're finding a probability to answer the question. Confidence intervals are designed to answer the question, what values of the population parameter would not surprise me? So you get a range. This is what is important to know. These are how they're related. Computing a 95% confidence interval is equivalent to doing a two-sided hypothesis test with alpha 0.05. So here's kind of how I think about it. Here's our hypothesis test. Suppose we're trying to figure out, is the mean 100 or is it not 100? So if you had like a normal distribution, this is kind of why I make you draw a picture. If you had a normal distribution, let's pretend your sample, x bar, was 105. That would go like right in the middle. Right? If you're doing a 95% confidence interval, you're saying the middle 95%, if this is true, is from 103.61 to 106.39. So your 95% confidence interval is the middle. Remember how we shade in a two-sided test? That's your rejection region, if you get any numbers in those regions. Do you see where 100 would fall? Would 100 fall in your shaded part or your non-shaded part? Shaded. That's why we call this the rejection region. So 100's here, so we reject our null hypothesis. So also you could just, if you don't think about, I'm a visual person, so I like the picture. If you just look at the interval, is 100 in the interval? No. So we're saying this is not true because we didn't get 100, so this is what's true. Now, it's probably greater because our interval is greater than 100, but we don't know that for sure. That's not what we're testing. We just know it's different. So if you're looking at the same hypothesis test, now let's pretend we get a sample of 101. So now our picture, we're still doing a two-sided test. Our mean is in the middle at 101, but our 95% confidence interval goes from 99.6 to 102. Where does 100 fall in here? In the shaded or non-shaded? The non-shaded. So this is why we would fail to reject our null hypothesis. Because 100 is a plausible value in our confidence interval. So that's why I have you draw it. what you're drawing is like where your null hypothesis goes. So if you're doing a one-sided test and alpha is 0.05, the decision's not always consistent with 95%. It's really, you got to do a 90% to make them equivalent. You want 5% on each side. So if you're doing a one-sided test, you're doing a 90% confidence interval. Okay, this works nicely but for means, but not for proportions. Because with proportions, the standard deviation calculations are different. In a confidence interval, we use p hat for our standard deviation. So in a confidence interval, you guys probably don't even know this, but you do p hat 1 minus p hat over n. But in a hypothesis test, we use p 1 minus p over n. So because these are different, in a confidence interval, you don't have a p-value because we're not comparing it. So it doesn't. This whole situation doesn't work as well. But the biggest thing to take away is that a confidence interval and a two-sided hypothesis test are related. They're basically the same. You're just answering different questions based on doing two different things. Questions on 10.5.
Should we do the time, like the conditional probability on the other side as you wrote?
Where?
Just want to write that down.
Oh. Oh, this part.
Yeah.
Got it.